Hello class, welcome, and today we are going to start the next video and the next section, which is 3.5 on rational functions. We're going to talk about graphs, applications, and models. And so now a rational function is when you have any two polynomials that are divided together. So in this form we have f of x equal to p of x divided by q of x, where obviously q of x cannot be equal to 0. This is what we're going to define as a rational function. So here are some examples of what we would call rational functions. You could have a constant divided by a variable. You could have a linear divided by a quadratic or two quadratics or other degree polynomials. And then since any values of x such that q of x is equal to 0 are excluded from the domain of a rational function, so these are our restricted values, okay, we're going to have discontinuous graphs. Okay, we could have often, not all the time, but often we have a discontinuous graph. That is a graph that has one or more breaks in it. It could be a hole in the graph, or it could be, and what we're going to discuss later is asymptote. So the simplest rational function is 1 over x. So this is the reciprocal function. This is one of those basic functions that you're going to want to know. Okay. So now the domain of this function is the set of all real numbers except for 0. Okay, because obviously 0 can't be in the denominator since you can't divide by 0. Okay, so now it's helpful to find the values of f of x as you get closer and closer to 0, so we can find out what the behavior is going on. We use the table feature on your graphing calculator to do this. Okay, so this is something, again, you could use at home. Obviously, we won't be able to use this on the exam, but something that you can use at home or with the homework and things like that, so for understanding. So in this example here, if you notice that as you get closer and closer and closer to 0, see how this is getting closer to 0, the y value is getting larger and larger and larger negative. So as you get closer and closer to 0 from the negative side, it's going to negative infinity, it seems like. And here, as you get closer and closer to 0 from the positive side, it's going bigger and bigger and bigger positive. Okay, so it seems that as x approaches 0 from the left, the function is going to negative infinity, and as it approaches 0 from the right, it goes to positive infinity. Now, the symbol x arrow 0 means as x approaches 0 without necessarily ever being equal to 0. Okay, so we just care about what's going on as it approaches 0. Since x cannot be equal to 0, then what will happen is this function will never intersect the vertical line x equals 0. So in other words, the y-axis. Okay, this is what we call a vertical asymptote. As the absolute value of x increases without bound, the value of f of x gets closer and closer to 0. Okay, so now we're going to look at the end behavior of the graph. Okay, notice that as what happens when x gets really, really big negative or really, really big positive. Okay, that's what we're looking at now. So as we can see, as x gets really big, either positive or negative, f of x is getting closer and closer to 0. Okay, so that means in this case here, it's going to be ever getting closer to the line y equals 0, or in other words, the x-intercept, but it will never cross the x-intercept, okay? Or excuse me, cross the x-axis, okay? So this is y equals 0, so the line is getting ever closer to the x-axis, but it will never cross, okay, or touch. So this is called a horizontal asymptote. So here's what it looks like. Okay, so if you graph this, notice that if you put those four things together, so as you get closer and closer to 0 from the right, it goes to positive infinity. And as you get farther and farther away from 0, or you go farther and farther closer and closer to positive infinity in the x direction, it gets closer and closer to 0. So it does something like this. And the same similar something here does this. Okay, and so we find that the domain is everything except 0. So this is the domain. And then the range is everything except 0. So notice that in the range, all values are accounted for except for y equal to 0. And in the domain, everything is accounted for except for x equals 0. Okay. And we say that it is discontinuous at 0 because there's obviously a break. So we have a vertical asymptote here, and we have a horizontal asymptote here. That's going to be important for graphing. Okay. It is also an odd function because, as you can see, if you rotate this 180 degrees, you get the exact same function back. So this is symmetric with respect to the origin, and therefore it has to be an odd function. Okay. So now here's an example. So graph the function y equals -2 over x. Now we want to give the domain in the largest open intervals of the domain in which the function is increasing or decreasing. Okay, so the domain in this case is going to be what? Well, it's going to be everything except for 0 again. Okay, so the expression -2 over x can be written as -2 times 1 over x. Okay, or 2 times 1 over -x. It doesn't matter. Usually just take the negative out. But indicating the graph may be obtained by stretching the graph of y equals 1 over x, okay, vertically by a factor of 2, right? So we could see that this is a vertical stretch, okay? And it's also a reflection if you take the negative out, okay? So we're reflecting across either the x or the y axis depending on where you put the negative sign. But in this case, you're going to end up with the same graph. Okay, so the x and y axes remain the horizontal and vertical asymptotes, and the domain and range is the same. Everything except for 0. And this is what you get. Okay. So we see that when we flip it across the x or y axis, we get this. Now, so that means that, as you can see from the graph, this is ever increasing. Again, as we move from left to right, this is ever increasing among the whole number line, except for at 0, right? So it's increasing here, and then here it continues to increase. So even though there's a break in the graph, it starts way down here and starts increasing. Okay? So now what about this one? Well, look at this. Now what's happening? Think about what's going on here. We're inside the function now. So we're adding 1 inside the function. So we can look at this as a horizontal shift. Okay? So this is a horizontal shift to what direction? We're going to the left. So this would be the same as taking 2 over x, right, the graph that we just got, taking this graph and then shifting it over to the left 1 unit. Okay? So if we start with our basic function 1 over x, we're going to shift it, or excuse me, stretch it by 2, and then we're going to shift it over to the left 1 unit. And so now look what happens to our asymptote. Our asymptote shifts over to the left 1 unit as well. So now our asymptote, our vertical asymptote, is at x equals -1, and our horizontal asymptote is still the same at y equals 0. Now, in this case, when we look at the range and the domain now is what? The range, or excuse me, the domain is now everything except -1, right? Because it shifted over 1. So now this is our domain. Our range is the same, didn't change. It's still going to be everything except 0, right? So if you look at the range, everything is covered except for the middle. Now what about this function? So here we have the rational function. This is the reciprocal squared function. So this is 1 over x squared. Now notice that the domain, again, is everything except 0 because 0 cannot be in the denominator. So even for this function, the domain is everything except 0. Okay. Now, with the range, though, it's going to be a little different because look at what happens as we get closer. Okay, so let's look what happens here. So as we get closer to 0, what's going on? As we get closer and closer to 0 from the left, this is going to positive infinity. And also when we get closer and closer to 0 on the right, it's going to positive infinity. So both of these are going to positive infinity. And as x gets really, really big, positive or negative, it's going to 0 again. Okay, so that's going to help us graph these. Okay. So this is what it looks like. So if we look at the map or the graph of 1 over x squared, again, this should make sense since all negative values of x are all going to be positive. So we have nothing below the x-axis. And so the range is going to go from 0 to positive infinity. So the domain stays the same as before with the other reciprocal function. So this is the reciprocal squared function, if you will. And this is what the function looks like. Okay, now, so what happens here is this increases from negative infinity to 0, and then decreases from 0 to positive infinity. And there's a discontinuity at x equals 0. And there's also a y-axis. The y-axis is the vertical asymptote, and the x-axis is the horizontal asymptote. Now this is an even function, as you can see. It is symmetric with respect to the y-axis. So this is an even function. So if we look at this example, now what do we got going on? Look at the basic function. We've got 1 over x squared, right? So this is a squared function, so we know it's going to behave like a reciprocal squared function. Okay. So, but what's going on here? Inside, we're adding 2 units. So this is going to be a horizontal shift to the left, 2 units. And we're subtracting 1 outside this function. And so this is going to be a vertical shift downward 1 unit. So we take the basic function, this, and we're going to move it to the left 2, and we're going to move it to the right, or excuse me, down 1. And so we also have to move the asymptotes along with it. So now notice that the intersection here of the asymptotes also moved down 1 and over 2. And the asymptotes have also moved down 1 and over 2, okay, to the left. Okay, and so that gives us this picture. So now we got to draw the dotted lines showing the asymptotes. We don't want to forget the asymptotes. Always make sure you plot the asymptotes. And so in this case here, the domain are all x values except for x equals -2. Okay, and that gives us this. Okay, so that gives us this. And while we're going to go down a vertical shift, the range is now going to start at -1. So it's going to be from -1 to positive infinity, not including, obviously, -1. And so again, this is going to be increasing from negative infinity to -2, and from -2, or it's going to be decreasing from -2 to positive infinity. Okay, and so the vertical asymptote is that x equals -2, and the horizontal asymptote is y equals -1. So now asymptotes. If we let P of x and Q of x define polynomials, consider the rational function f of x equals P of x divided by Q of x, written in lowest terms, okay, key, written in lowest terms, and real numbers a and b. Okay. 1. If the absolute value of f of x approaches infinity as x approaches the value a, then the line x equals a is a vertical asymptote. If f of x approaches b as x approaches infinity, the absolute value of x approaches infinity, then the line y equals b is a horizontal asymptote. So that's how we see where the horizontal asymptotes are. That's what we've been doing in the last few slides. Okay. Now, determining asymptotes. Okay. So here's what we have to do. Once we express the rational expression in lowest terms, then we follow the following procedures. Okay, so 1, vertical asymptotes. Find any vertical asymptotes by setting the denominator equal to 0 and then solving for x. Okay, if a is a 0 of the denominator, then the line x equals a is a vertical asymptote. That'll always be the case. Okay, if a is a 0 of the denominator, so that when you take the expression in the bottom, set the bottom equal to 0, solve it, and then if you get a 0, okay, whatever value you get that makes the thing equal 0, that's going to be where your vertical asymptote is located. Now, other asymptotes, okay, determine any other asymptotes by considering 3 possibilities. If the number is lesser degree, so if the numerator, if the numerator has a lesser degree than the denominator, then there is a horizontal asymptote at the y-axis, or the x-axis. So y equals 0. So again, if the degree of the numerator is less than the degree of the denominator, then the x-axis is a horizontal asymptote. B, if the numerator and the denominator have the same degree, then the function is of the form given by this, right? This is the same degree, right? Then what happens is the horizontal asymptote is actually the ratio of the leading coefficients. And the basic reason why that is because as x gets really, really, really big, the controlling feature of the top and the bottom is going to be the first term. So if x gets like really, 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 really big, then what's going to happen is this fraction is going to get closer and closer to just this, which is going to be reduced to a of n over b of n. And so that's why we can say that conclusion. Okay. So if the degree of the top is the same as the degree of the bottom, then you take the ratio of the leading coefficients, and that is going to be where your horizontal asymptote is located. And then the third thing is, if the degree of the numerator is exactly 1 more than the degree of the denominator, then there's going to be a slanted asymptote. And what we do, in order to find it, we're going to have to divide. Okay, we're going to have to divide the numerator by the denominator and then disregard the remainder. And so what we're going to do is we set the rest of the quotient equal to y to obtain the equation of the asymptote. Okay. In other words, if there's an oblique asymptote, then if we want to find what it is, we divide the numerator by the denominator, and then we get the quotient plus remainder. We disregard the remainder, and whatever the quotient is, that is the function of the asymptote. Okay? So note, the graph of a rational function may have more than one vertical asymptote, or it may have none at all. The graph cannot intersect any, keyword, any vertical asymptote. There can be at most one other non-vertical asymptote, and the graph may intersect that asymptote. Okay. So in other words, horizontal asymptotes may be intersected at times. Okay, so it is possible to cross over a horizontal asymptote or a non-vertical asymptote, but never a vertical asymptote. So now it says, give the equations of any vertical, horizontal, or oblique asymptotes for the graph of this rational function. So right away, notice that this denominator becomes 0 when x is 3, or when x is equal to what? 1/2. Okay. So what does that tell you? That means that we're going to have some vertical asymptotes, because as x approaches 1/2, this thing's going to infinity. As x approaches -3, this is going to infinity. Okay, so there's going to be asymptotes, vertical asymptotes at x equals 1/2 and x equals -3. There's also going to be a horizontal asymptote. Hold on a second. Yes, there's going to be a horizontal asymptote at x equals 0. Or excuse me, I'm sorry, y equals 0. Okay, because the degree on the bottom here is 2, because if you multiply this out, you get x squared. So it is a squared term on the bottom. And so that tells us, since the degree is larger on the bottom, the asymptote, there's going to be a horizontal asymptote at y equals 0. Okay. Okay, so this is what we got before. Now to find the equation of the horizontal asymptote, we're going to divide each term by the greatest power of x in the expression. So this is another method. Now remember, if you use the shortcut or the idea, it already said that if the denominator on the top is less than the denominator on the bottom, then we know that there has to be a horizontal asymptote at the x-axis. But we can also find out by dividing. So let's divide. Okay. So we change it into this form. And if we divide, or if we multiply the top and the bottom by the largest power of the denominator, that's the key. Okay. We want to divide each term by the greatest power of x in the expression. Okay. The largest power of x is x squared. So if we divide everything by x squared, we get this. And so what happens here? Well, this simplifies to 1 over x. This simplifies to 2. This simplifies to 5 over x. And this becomes minus 3 over x squared. Okay, and then leave it in this form. Okay, now what you're going to do is, now what's going to happen is, okay, what happens as x gets really, really big? Okay, well, when x gets really, really, really big, right, we're looking for horizontal asymptotes. So when x gets really, really big, what's going on with the function? Well, if this gets really, really big, this is going to go to 0, this is going to go to 0, this is going to go to 0, and this is going to go to 0. And so what we're going to end up left over with is 0 over 2, which is 0. Okay, so this tells us exactly what we suspected, is that the x-axis is the horizontal asymptote. Okay, so now look at this here. Okay, so now this one, if you notice, has a vertical asymptote at x equals 3, right? Set the denominator equal to 0. So x is equal to 3 is a vertical asymptote. And because these both have the same degree, we could take the ratio of the leading coefficients, which is 2 over 1, and we see that there is a horizontal asymptote at y equals 2. But again, we could use division, and we could divide the top and the bottom by the largest power of x, okay, and do the same thing. Okay. And so here's what we do. So they divide the top and bottom by the largest power of x, which is just x. And so we get 2 plus 1 over x. So this goes to 0 as x gets really big. And this gives us 1 minus 3 over x, which also goes to 0 as x gets really big. And so what happens is this, you get 2, which is exactly what we got. So now what about this one? Now here we've got the denominator, or the numerator degree. The degree of the numerator is exactly 1 more than the degree of the denominator. Now, so that means there are no horizontal asymptotes, but there may be an oblique asymptote. Okay, we'll have to look at it. So let's analyze this. So we know that there's going to be a vertical asymptote at x equals 2 because of the denominator. And if we look at this and we divide the top and the bottom by x squared, what do we get? We get this. Okay, so we divide everything, we get 1. We get 1 over x squared, so this goes to 0, this goes to 0, and this goes to 0. So when this goes to 0, what's happening to this? This is going to 1, right? This is going to 1, and this is going to 0. Well, as this goes to 0, this has to be getting bigger, right? The whole thing is going off to infinity, right? Because the denominator is getting closer and closer and closer to 0, right? So as x approaches infinity, okay, does not approach any real number. So f of x is approaching infinity as x approaches infinity. Okay? This happens whenever the degree of the numerator is greater than the degree of the denominator. In such cases, we want to divide the denominator into the numerator to write the expression in another form. So if we use synthetic division, we're going to get this. So we get our remainder, which we're going to ignore, and then this gives us our quotient. And so what happens here is we get this plus this. And so what this tells us is there is a slanted asymptote at x plus 2. Okay? This is what we call, again, an oblique asymptote. And the reason why we can do this is because as x gets really, really, really big, this is going to 0. And so this gets closer and closer to the value of x plus 2, right? Because that last remainder is going to 0. So that's why we don't want to include it. Okay? So this line is an oblique asymptote, slanted. So it's obviously neither horizontal or vertical. for the graph of the function. And so here are the steps. So to have a comprehensive graph of a rational function, we're going to basically show the following characteristics. One, all x and y intercepts, got to find those, right? So that's going to be part of the graphing process. Then you also want to find and map all of the asymptotes, vertical, horizontal, and or oblique. Okay. 3, the point at which the graph intersects the non-vertical asymptotes. Okay. At which point does it intersect the non-vertical asymptotes? Okay. If such a point exists. And then 4, the behavior of the graph on within each domain of the interval, right? So we're going to split this up in intervals, and we're going to test each interval, okay, to determined by the vertical asymptotes and the x-intercept. Okay. So if we use this example here, so we let p of x, f of x equal p of x over q of x, define a function where p of x and q of x are polynomial functions, and the rational expression is written in lowest terms. We want to sketch the graph using these steps. Step 1, find any vertical asymptotes. Step 2, find any horizontal or oblique asymptotes. And then 3, find the y-intercept by evaluating the function evaluated to 0, so when x is 0. 4, plot the x-intercepts, if any, by solving for f of x equal to 0, right? So in other words, the numerator equal to 0. Okay. 5, determine whether the graph will intersect its non-vertical asymptote. Okay, so what happens as x approaches that value? Okay, find out. You need to find out. Okay, make sure you know that. 6, plot selected points as necessary. Choose an x value in each domain interval determined by the vertical asymptote and x-intercepts. Okay, and then complete the sketch when you're done. So now, for example, if we look at this, we've got x plus 1 divided by 2x squared plus 5x minus 3. So notice that the degree on the top is less than the degree on the bottom. So we know we're going to have a horizontal asymptote at y equals 0, so the x-axis. Okay, so let's see if we can factor this, because we want to see if anything cancels, because we want to make sure this is in lowest terms, right? That's one of the conditions. So it does factor into these, okay, so nothing cancels. But we also now know where the vertical asymptotes are located. So in this case here, because of the zero product principle, we've got a vertical asymptote at x equals 1/2, and we've got another asymptote at -3. Okay, so now the y-intercept is at -1/3. How would we get that? Well, we're evaluating it at 0. So all of the x terms, all the terms with x are 0. And that leaves us with 1 divided by -3, which gives us the -1/3. Okay, that's easy peasy right there. Okay, so that's where we get that. And then the x-intercept can we find by setting this whole thing equal to 0. Well, the only time that this is going to be equal to 0 is when the numerator is equal to 0. So if we set that equal to 0, we get the fact that it will happen when x is -1. Right? There we go. Now, to determine whether the graph intersects the horizontal asymptote, we're going to solve what? F of x equal to 0, the y value of the horizontal asymptote. So what we're going to do is we're going to find out if it intersects the horizontal asymptote at all. And we see if there is an x value that makes it 0. So since the horizontal asymptote is the x-axis, the solution to this equation is when y is 0. Okay, so the solution of this equation found in step 4. Okay, that's what we found. The graph intersects its horizontal asymptote at x at -1, 0. Okay, so let's say that again. To determine whether the graph intersects its horizontal asymptote, we want to solve, in this case, see if the function is ever equal to that value at any point. Okay, if it is, then the graph intersects it. If it doesn't, then the answer is no. So we take this value and we basically solve for x equals 0, or excuse me, for the function equal to 0, and see what we get. Okay. Now, since the horizontal asymptote is the x-axis, the solution of this equation was found in step 4. So we already got that from step 4. Okay. The graph intersects the horizontal axis at -1, 0. And then we're going to plot each point in the interviews determined by the x-intercepts and the vertical asymptotes to get an idea of how the graph behaves within each interval. And so within this space, right, so we've got, if we look at this, hold on. If we look at this here, right, so we've got a vertical asymptote at what? 1/2 and -3, right? Okay. Okay. So in this graph here, oh, hold on, back. So step 6, oh, we did this already. So here we go. So here's our interval. So we're going to go from -infinity to -3. That's the first asymptote. Then we're going to go from -3 to -1. Okay. That's we're going to have the where the graph intersects. Okay. And then we're going to go from -1 to the 1/2. That's going to be the other asymptote. And then we're going to find what's going on in the fourth region, which is from -1/2 to infinity. So what do? We evaluate a test point. So we pick a test point within each one of these, and we evaluate the function at that test point. Here, we get a negative number, right? Here, we get a positive number. So the next thing is we look at the positive and negative. And so if it's negative, we know we're below the x-axis. If it's positive, we're above. And so that tells us how to sketch this thing. And this is what we get. So step 7, once we know, so here, this point is below, that means we're going to be below this graph always. Okay? Also, we know that this is our test point, but we also know that it crosses at -1, 0. Okay, because we solved it for that. And then, of course, we have our test point here, which is above. So here, we can't go past the vertical asymptote. So in other words, it's what this does is it goes from high all the way down through here, all the way down to the right. So this is what this is going to happen. And then in here, it's all above the x-axis. Okay, and so that's how we sketch these. And notice that we've got the vertical asymptote and, of course, the horizontal asymptote, which is the x-axis. Okay, so let's see here. We've got degrees are the same, right? And says steps 1 and 2 is determined by example 4b. The equation of the vertical asymptote is x equals 3. Okay, and the horizontal asymptote is at y equals 2. And f of 0 is -1/3 again. Okay, so the y-intercept is at -1/3. And then we're going to solve for f of x equal to 0 to find any x-intercepts. And so this is going to be true when 2x plus 1 is equal to 0. Okay. And so we get x equals negative 1/2 as the x-intercept. Okay, so what's next? Step 5, we're going to graph does not intersect. So the graph does not intersect its horizontal asymptotes. It's f of x equal to 2 has no solution. So again, the horizontal asymptote is located at y equals 2. So again, to solve this, to see whether it crosses the horizontal asymptote, we're going to set this equal to 2 and see if we can get an answer and try to solve it. Okay? So here's how we do it. Set it equal to 2. Then we multiply by the denominator, and we multiply both sides of the equation by x minus 3, and we get this. And then what do? We solve for x. And look at that. The x's cancel out, and we get 1 equals negative 6, which is a false statement. In fact, there is no x's. And what this tells me is that there are no solutions to this. Right? There's no x value that will make this true. And so then what we do is we take the points, okay? Negative 4, 1, 1 comma negative 3/2, and 6, 13/3 are on the graph, and we basically use the information about the asymptotes to complete the sketch of the function, which is decreasing on every interval, as you can see. Now, what about this one? So here we have another complicated looking polynomial. And so again, we've got the top and the bottom, the degrees are the same. So we know that there's going to be a horizontal asymptote at y equals 3. Okay. But we could also see about factoring this thing, because remember, we want this in lowest terms. So let's factor this, or not factor, but let's see if we can figure out a way to reduce this. If we do it with factoring, that's fine. But we want to make sure this is in lowest terms. Okay, so to find the vertical asymptotes, we're going to solve for x squared plus 8x plus 16 equals 0. Okay. And so we get x plus 4, quantity 2 is 0. So x equals negative 4. Okay, so x equals negative 4 by the zero product principle. Now to find the vertical asymptotes, we're going to set that equal to 0. So we got, the vertical asymptote is going to be at x equals negative 4. Okay, since the numerator is not 0, when x equals negative 4, the vertical asymptote has the equation of x equals negative 4. Okay. And then we're going to divide all the terms by x squared and consider the behavior of each term as x approaches infinity. And so we'll see what happens. So we're going to divide everything by x squared. Right? And by doing that, we're going to end up getting the leading coefficient of the top and the leading coefficient of the bottom. And this should be something that you should study and know. So all we have to do is take the ratio of the leading coefficients in this case. Okay, so in this case it's 3. So y equals 3 is where the horizontal asymptote is located. Okay, now the y-intercept is located at where? It's going to be negative 6 over 16, which is the same as 3/8, negative 3/8. Then find the x-intercepts. We're going to set the whole thing equal to 0, but realistically it's just the top is equal to 0. And so how do we solve that? Well, I would factor out a 3 and divide by that. Okay, let's see here. Okay, so now we're going to set this. Now when we solve this, we're going to get this here because we divided by 3 to get rid of the 3 in the leading term. And so now that we have this, we can factor this by using the AC method, and we see that we get x minus 2 times the quantity x plus 1. And so we get x equals 2 or x equals negative 1. Okay. And so the x-intercepts are negative 1, 0, and positive 2, 0. We set f of x equal to 3 and solve to locate the point where the graph intersects the horizontal asymptote if it does. And so we set it equal to 3, and then we solve this thing. Okay. And so we're going to multiply each side again by the denominator, and we get this expression. And then we're going to simplify it. Right? So we're going to subtract the 3x squared. So notice that we get 3x squared here and 3x. So those are going to go away. And we end up with this. And so now we can combine like terms. We get negative 27x is equal to 54. And we get x is equal to negative 2. And that is where our vertical asymptote is located. Or excuse me, I'm sorry. This tells us that it crosses the horizontal asymptote because we set it equal to, where was it? We set it equal to 3, I think. Yeah. And so we found a value of x that makes that true. So that means it crosses the horizontal asymptote at x equals negative 2. So the point that intersects the horizontal asymptote is going to be negative 2, comma 3. And so when we put it all together, we sketch the graph, and we figure out what the behavior looks like. Okay. So now the behavior of the graphs of rational functions with vertical asymptotes. So just be aware, these are the different ways that you could have behavior. Okay. So suppose that f of x is a rational expression in lowest terms. If n is the largest positive integer such that x minus a to the n is a factor of the denominator of f of x, okay, the graph will behave in the manner illustrated. Okay. So it could behave like this. It could behave like this. It could behave like this or this. Okay. Now we also have observed that the behavior of graphs of a polynomial function near its zeros is dependent on the multiplicity of the zero. Remember that. So does it cross? Okay. Or does it bounce? Okay. So it's dependent on the multiplicity of the zero. The same statement can be made for rational functions. Okay. Suppose that f of x is defined by a rational expression in lowest terms. If n is the greatest positive integer such that x minus c to the n is a factor of the numerator of f of x, the graph will behave in the manner illustrated. Okay. If n is 1, then we're going to get it crosses somehow. Okay. If n is even, it's going to bounce. Okay. Either up or down. And if n is odd and greater than 1, then it's going to cross at c. Okay. So what about this one? Now here we have a denominator that is 1 degree larger on the top than on the bottom. Okay. And so what do we have here? Well, we're going to have an oblique asymptote. So if we divide this, we're going to get, well, we have a vertical asymptote at x equals 2, right? Looking at the denominator. If we divide these two, we're going to get a oblique asymptote at y equals x plus 2. Okay, the y-intercept is at -1/2. Okay, and the graph has no x-intercepts at all, since the numerator is this. So there's no value that will make this 0. There's no value of x that we can plug in and make this 0. So there is no x-intercepts in this case. So it has no real zeros. Okay, so the graph does not intersect its oblique asymptote either. Okay, so if you set this equal to the oblique asymptote and solve, see what we get for what we get. And if you solve this, you're going to get where the x's are going to drop out and you're going to get a false solution again. Okay, and then using the y-intercept, the asymptotes, the points that were given, which is 4, 17.5 and -1, 2/3, -2/3, and the general behavior of the graph when you get closer to the asymptotes leads to the following graph. Okay, so notice that it fits right in this triangular region on the top and over in the bottom. Now, a rational function that is not in lowest terms often has a hole or a point of discontinuity in its graph. So if we look at this one, okay, we can see that this is not going to be in lowest terms, and we see that there is something going on. There's a restricted value at x equals 2. Okay. Well, we also notice that we can factor the top. Okay. And if we factor the top, look what happens. This cancels with this, and we get x plus 2. Which means that it seems that the discontinuity goes away, right? Well, no, it doesn't. Okay. This is what we call a removable discontinuity. Okay. Or it is a hole in the graph. Okay. And it's just that when we reduce it to lowest terms, we don't see this anymore. Okay. So we want to make sure that we look at the domain of the function before we reduce it. Okay. And so the domain is going to be everything for x, everything except x equals 2. Okay. So we get the straight line that looks like this, except at x equals 2 we have a hole. Okay. So here's one example of where we would use analysis for this, traffic analysis. So it says vehicles arrive randomly at a parking ramp at an average rate of 2.6 vehicles per minute. The parking attendant can admit 3.2 vehicles per minute. However, since arrivals are random, lines form at various times. A. The traffic intensity, X, is defined as the ratio of the average arrival rate to the average admittance rate. Determine X for this parking ramp. So the average arrival rate is 2.6 vehicles, and the average admittance rate is 3.2 vehicles. So if we just take the ratio, we find that the intensity, the traffic intensity, is 0.8125. Okay. B, the average number of vehicles waiting in line to enter the ramp is given by this function. Okay. Where x is somewhere between 0 and 1. Could be 0, but less than 1. Is the traffic intensity. Graph f of x and compute f of 0.8125 for this parking garage. Okay, so if you do this on the graphing calculator, Okay, you can sketch this, but on the graphing calculator, you can see how this works. So if you graph it and then use your value key, you can find the y value when x is equal to 0.8125. And we find that the value is 1.76 vehicles. So the average number of vehicles given by that function. So given the intensity x, the average number of vehicles waiting in line will be approximately 1.76 or somewhere between 1 and 2, right? What happens to the number of vehicles waiting as the traffic intensity approaches 1? Well, if you look at the graph the function as x approaches 1, this denominator is getting smaller and smaller and smaller, and it approaches 0, which means this thing is going off to positive infinity. Okay, as you approach 1. Thus, the average number of waiting vehicles gets very large, right, as the intensity gets closer to 1. Okay. Okay, so that ends this section. And so next time we'll continue with section 3.6 and we will finish up the chapter. And that will finish up chapter 3. And we're going to move on to the final chapter of chapter 4. Until then, have a great day, and I'll talk to you next time.